Good day, everyone. Welcome to our class for today. In today's class, we will be studying vectors. I believe that it's going to be useful if you pay attention and you follow through the examples that I will be working through in today's class. First, things to discuss. We want to understand the basic concepts and definitions. What is a vector? How do we describe vectors and all of that? We are also going to be discussing vector addition. How do we add two or more vectors together? Subtraction. How do we subtract two or more vectors? And scalar multiplication. We would go ahead to study unit vectors and Cartesian representation. We would then go on to scalar product, and we would do some examples on calculating scalar product. Scalar product is also referred to as dot product. Finally, we would end with vector product. Vector product also referred to as cross product, all right? And we'll see examples. Basic concepts. What do we understand by vector? A vector, in short, can be described as an arrow in space. This shows direction and magnitude of such arrow. An example of a vector is what I'm going to be drawing here. You might have this line, call it the first line A, all right? And remember I said it's going to have direction. So this arrow indicates the direction, and it's going to have a magnitude. Let's say we start from origin and we end at a point P. So these vectors, let's call it vector A, and we put this arrow on. Tells us that the line or the arrow has a direction indicated by this triangle, and also because it starts from 0 to P, then we can actually obtain the magnitude of that arrow A. All right, the magnitude is usually represented with this in this way. So this tells us the difference between a vector and vectors. Like, let me say it one more time. It's going to have direction and it's going to have magnitude, or the length of such arrow. Another concept which I would want you to understand is the concept of negative vector. Negative vector is simple to understand. I've drawn this line or this arrow and I've called it vector A, all right? Let's draw a separate arrow, okay? And let's make this triangle face back. That means we want to move from, let's call this from point A here, and this is point B. So the negative of A is going to be minus A, all right? So this is the negative of vector A. So we are given a vector A. The vector which is the negative of A is a vector in the opposite direction. And remember, we always indicate the direction with this triangle. But it's going to have the same magnitude as A. That is, it's going to have the same length as A. However, the direction is only going to differ from A. That is the negative vector of A. What do we understand by equal vector is another term. Equal vectors, given two vectors, you say these two vectors are equal if they have the same magnitude. Please take note, if their lengths are the same. Suppose we have vector A and vector B. We're going to say A and B are the same. A is same as B, that is vector A is the same as vector B, if and only if they have the same magnitude, that is the magnitude of A is equal to the magnitude of B, and the direction of A is the same as the direction of B. Then you say vector A and B are equal vectors. These are basic concepts that we need to understand. Okay, we're going to go on to vector addition. These are algebraic operations that we sometimes perform on vector. We perform operations such as addition, subtraction, even multiplication. All right. So let's start with addition. The addition of vectors is defined by triangle law. And I've taken time to describe again what triangle law means. Suppose we have two vectors A and B. If they are placed such that the trail of B starts at the end of at the edge of A, then the vector from the tail of A to the head of B represents the resultant vector. I'm going to indicate it geometrically for you to understand what I'm talking about. Suppose we have a vector A. Say this is vector A. This is the tail of A, right? And then this is the head of A. We call this vector A. Okay? And if we have another vector B, such that vector B, the tail of B, starts at the head of A. So this is the head of A, and this is the tail of B, which is another vector. So we call this vector B, right? Now we have joined two vectors, A and B, together. Recall that the head of A, it's where the tail of B is joined to. Now the resultant of these two vectors is usually known as the addition of the two vectors, which we go on in that way. So that is how we had these two vectors, and we call it the resultant vector. All right. And in this case, we're going to be using the triangle law to obtain the resultant R. And this is the resultant shown mathematically here. Sorry about that. I'm going to delete that. So that is how we add vectors together. Two vectors. We can add two vectors, we can have three vectors, we can have more vectors. All right. And that is the example I've drawn here on this slide. We draw vector A, and then we start from the head of A to draw vector B. The vector from the tail of A to the head of B is the resultant, like I've shown you in the previous slide. What does the triangle law help us to do? It helps us to visualize the addition of vectors, and it's fundamental and this is fundamental in physics and engineering. In order to understand vector quantities, for instance, we can use this for forces, for velocities, for displacement computation. All right. Here's an example. I'll walk you through this example and I'll represent it geometrically as well. Suppose we have P to be a force of 40 Newton. This force is acting in the direction due east. All right. If you go to you can indicate your north. We want to indicate This is your pole. So we want to see in what direction. The question says if P is a force 40 Newton acting in the direction due east. So we can actually draw a line in this direction east. Okay, say that is P. And Q is the force of 30 Newton acting in the direction due north. So we want to go from the head of P in the direction due north, that is Q in that direction. Okay? The question now says, what is the magnitude of the vector sum R of these two forces? Remember from our definition and using the triangle law, the resultant between these two forces is the sum, right? Which is R. Beautiful. These two forms angle 90 with each other, and therefore we can simply calculate R using the hypotenuse, that is the magnitude of R using our hypotenuse Pythagoras equation rather. But before then, let us compute what R is. How do we know what R is? We know that P is 40, that is, it goes from 40 to 0, and then that is what this means is when you have coordinates, you have x and y. I believe you still remember that. Okay, so 40 is on the y-axis, 0 is on the x-axis. So we have 40 here, and then we also have q to be 0, x-axis is 0, y-axis is 30. So it's 0 and then it's 30. Okay, so let's obtain R. R is simply going to be what? R therefore is 40 and 0 plus 0 and 30. Okay, and how do you do this sum? You had 40 to, that will be 40, and you add 0 to 30, that will be 30. So here what we do is we had this to this, and we had this to this. That is how we do vector addition. Okay, and that gives us 40 by 30. That is, R is going to be 40 by 30. But then, what is the magnitude? Remember, magnitude implies what? The length of that vector. So what is the length of vector R? To obtain the length of vector R is where we use the Pythagoras theorem. Don't forget your Pythagoras theorem is R squared equal to x squared plus y squared. And in this case, our x is 40, while our y is 30. And that is why we have 40 squared plus 30 squared. Okay, 30 squared. And in order to have only r, you take the square root of the right-hand side. So you take the square root of this, will give you only r. And when you do that, our final answer becomes 50 Newton. I hope you do understand how to obtain the magnitude of a vector. The magnitude of that vector, r, which is the resultant of these two forces, these two vectors, would be the square root, that is applying the triangle law, becomes the square root of x squared plus y squared. How do we then perform vector subtraction? It's similar to the way we had done addition. The only difference here is negative vector becomes what we use. And don't forget I've described or I've defined what negative vectors are. Negative vector will simply be a vector going in the opposite direction. This is I'm going to illustrate this also geometrically so we can see what I'm talking about. Now let's consider this example for subtraction. Suppose we have a vector A, which is 3 by 4. Don't forget how to represent this geometrically. To represent this geometrically, when you say vector is 3 by 4, it implies x is 3, right? X, so this is going to be x comma y, and this is maybe x2 comma y2. Okay, so we have vector A to have coordinates 3 and 4, vector B to have coordinates 1 and 2. You can draw this geometrically. If you have start from origin 0, we can draw a straight line to show our x, and then this is 0, 1, 2, 3, 4, and so on. So this is your x-axis. Now we can also draw our y-axis to be label 1, 2, 3, 4, and so on. Okay. So this coordinates now, let's draw vector A. We have 3, 4. That's 3 up to 4. So this is point we're referring to, and our vector is this. So this is point we're referring to, and our vector is this, up to 4. So this is vector A. Okay, then let's vector B. It's 1 on the x-axis and 2 on the y-axis. So let's just indicate it as this point, which can then go from origin to that point. So we call this vector B. Now, what is then the resultant of these two vectors? The resultant will be the sum of the two vectors. But then we want to go from A to B, right? Remember, this is a point and this is another point. Let me draw it out clearly so that we see what I'm referring to. We have this is B, and then we have another which is A at this point. So we have it like this. So in this case, this is B, this is A. Now this is going to be the resultant between the two of them, this dotted line that I'm drawing. All right, so we call this R. How do we obtain R? R will be A plus B. But look at A. A goes in this direction. That's the direction of A. So here we're going to be having A plus B, which should be the resultant. However, we want to do from B and then up to A, it then becomes minus B. So we're going to go A minus, because we want to obtain the negative side of it, minus B. And that means we're going from here way to this point. So in that case now, you see that B all of b, which is 1 comma 2, will then become negative minus 1 comma 2. And what is that going to be? It will be a minus, that is what is, let's just use the values here now. Using the values that were given, we see that a is 3 by 4 plus. So what we're doing is addition, but we are, because b is going in the negative direction or the reverse direction, so it becomes a plus negative b, and negative b now is minus 1 and minus 2, because that is going to show us in the negative direction of the initial direction of b. So that is a minus b, and we're going to be working with this equation. All right. So from this equation, you see it's going to be 3 plus minus 1, like I did in the first case. And it is 4 plus minus 2. All right. And then gives us a final answer 2 comma 2. That is the resultant of these two forces, but we are doing subtraction. Here we go on to scalar multiplication. A vector can be multiplied by a scalar, but before I go on, what we need to understand, scalar. Scalar will be one numbers. For instance, 1 is scalar, 2 is scalar, 100 is scalar, and k is scalar. C is a constant, which is scalar. So we have these as scalars, which are not vectors. Vectors can be represented using your coordinates, but a scalar is just one number, single number. So for this now, we want to see how we multiply our vector with or by a scalar, by a single number. Basically, when we do this, it's going to affect each element of the vector. Okay? And from these equations, let's look at how that happens. Suppose we have vector A and B, and we're performing addition between those two vectors. You can see the effect of multiplying the vectors by scalar. What happens eventually is K multiplies A and K multiplies B. The direction will be the same. However, this vector, each of the vector will be K times longer. Let's give numbers to K. Suppose K is 5, and we are doing 5 multiply vector A plus vector B. What will you have? You see that the result will be vector A being K times longer, that is Ka, while vector B would also be K times longer. So we said if K is 5, that My apologies, I'm having a bit of connectivity issues. Okay. My apologies, there was a bit of network hiccups from my side, and we're going to continue from where we stopped. We stopped here at scalar multiplication. So we want to go on with scalar multiplication and see the following examples. The example here is in a triangle ABC, as you can see in the figure below. M is the midpoint of A and B. M is the midpoint. Suppose AB, vector AB is denoted as vector A and vector BC is denoted as vector B. The question says express vector AC. How do we express vector AC? We'll see that shortly. AC from this diagram should be carefully noted as taking the direction of AB with respect to the direction of BC. Because now we see the direction of AB to point this direction, now the direction of BC, it's in this direction. All right. So AC will therefore be AB plus BC. Okay. No direction change is indicated here for AC because we're simply going in the direction of AB and going in the direction of BC. Hence, we can solve the problem using this solution. All right. The other question says, what is the vector CA? Now we are no more going in the direction AC, A to C. We want to go in the direction of C to A. Automatically, you note that going that direction C to A, let me just take out the other arrow which I had there. You should then note that going the direction C to A implies you are going in the reverse direction of AC. And going the reverse direction of AC implies you must have negative AC. There comes this solution. All right. And what is negative AC? Because AC from the first solution we had is A plus B. Then negative AC will be what? Negative A plus B, which then can be simplified as minus A minus B. And if you look at it carefully from the diagram, you see that going in the negative or reverse direction of B implies minus B, right? Plus, we're also going in the reverse direction of A, which then becomes plus minus A. If you're looking at the diagram to solve the problem. And this becomes minus B. This then becomes minus B minus A. The next question is, is do we have associativity between these two? Is minus AB the same thing as, is minus A minus B the same thing as minus B minus A? Yes, this holds. Okay, for scalar multiplication, it holds. All right. Let's go on to then obtain Cm. Cm is going to be, let me take out the, so that we have a clearer picture of Cm. So what is Cm? From the diagram, you can see C to M would be C to B. Let's write that down. C to B in the direction C to B plus B to M, and that is in the direction B to M. Okay, that then becomes our Cm. However, there are important things we need to take note of. Your vector has both magnitude and direction. So let's consider the directions now. The direction of CB implies that vector B is going in the negative direction. So it becomes minus B. While we note that M is the midpoint from the question, M is the midpoint of AB. Hence, we know now that BM is going to be, BM, let me just write it newly. BM should then become what? Half of AB. Because the question says is the half point or the midpoint of vector AB. Since that is clarified now, we're going to then look at the direction. If it goes in the same direction as vector AB, we would not make it negative. But because we want to obtain Cm, and Cm goes in negative direction of B, vector B, and also goes in the negative direction of vector A. Hence, we would have minus B to be Cm now, minus B, plus minus half of A. I believe you could see it from the diagram. Since BM is half AB and AB has been represented by vector A, hence we have Cm to be equal to negative half of vector A. And this is how we obtain that vector C here. I believe you can see it, it's clear, and I've taken my time to describe enough of that. We're going to introduce a new concept known as unit vectors. Units, it usually implies one. So when you say unit vectors, these are vectors that have a magnitude, that is length of one. They are usually denoted by a heart on top of the variable symbol. Suppose you're considering vector A. Suppose we're considering vector A, and you want to say the unit vector of A would then imply or will be represented in this form, heart of A. All right. So the unit vector in the direction of vector V or vector A will be given by the following equation. That is, V divides by the magnitude of V. That gives you the unit vector. We'll see this better with the following example. In this example, we're told to find a unit vector of this vector V, which is given as -3 and 5. First, I would like you to practice drawing your vectors geometrically. So for this vector V, we're going to be having it start from, remember I said this is X, coordinate X and coordinate Y. So on the x-axis, if you draw the real number line up to 0, let's say, and then continues to positive, this is going to be your -1. This is your -2. We just this is -2, and this is your -3. So x is at this point -3, and then you draw your y-axis on line 0. It's 1. So it's 1, 2, 3, and up to 5. So it's 5. Practice drawing this. So you're starting from here. It's you're going to start from origin in most cases. So you go in this direction. This is your vector V, and please don't forget to indicate the direction of the vector V. So this is what your vector V should represent. Now, I just did this so that you can learn how to practice drawing your vectors with respect to the direction. The question we want to answer here is to find the unit vector of V. We're going to simply be using the formula for unit vector as indicated here. And since V is -3, 5, 5, we would only be calculating the magnitude now. Don't forget the magnitude is the length of the vector. How do we calculate it? We use the triangle law. The triangle law then says by the law, Pythagoras law, R equal to the square root of x squared plus y squared. This is usually your formula for magnitude. This is addition plus. So what is x? X is simply -3. Substitute -3 into x. What is y? Y is 5. Substitute 5 into that equation. Then we have our magnitude to be computed as follows with this equation. All right. So our magnitude becomes square root of 34. But that is not all. We need to obtain the unit vector using the formula that we have here. So this formula now, if we want to use it, it becomes -3 divided by root 34, comma 5 divides by root 34. That is how you're going to be writing the unit vector, which is what I've marked. All right. And you can actually do a sketch of this unit vector. If you solve -3 root 34 with your calculator, you obtain a value for the x coordinate, and then you also simplify 5 over root 34 to obtain the value of y coordinate. And you simply draw it out like I did. All right. I think you understand what a unit vectors imply now. We then go on to Cartesian representation of these vectors. Cartesian would be I, j, k, that is with respect to the planes. Remember, we say we define our arrows in the space. So your space goes in different dimensions. It could be two-dimensional. If it is two-dimensional, then you would have x and y. coordinates. Okay, so this is your two-dimensional. I'll just call it 2D. If it is three-dimensional, it becomes X, Y, and Z. This is your three-dimensional space. Okay, how do we then represent our vectors in all these dimensional spaces? Suppose we want to do for three-dimensional space which has X, Y, and Z, which has X, Y, and Z, we're going to be using unit vectors I, unit vectors J, and unit vector K in our Cartesian coordinate system. I'm going to show you that in the next slide. So here we have any three-dimensional vector, any vector in a three-dimensional space can actually be represented as Vx. Remember, X, Y, Z indicate the space. For instance, this diagram we have here, this plot shows us Z coordinates, shows us X coordinates, and shows us Y coordinates. These are the three coordinates in the three-dimensional space. For two-dimensional space, like I mentioned initially, you're going to be having only X and Y, like the usual example we have dealt with before now. Okay, what does I represent? I is the unit vector I. J is the unit vector J. K is the unit vector K, which can be computed. All right, I believe you understand. Here is an example to describe further the Cartesian coordinate representation. Suppose we have a vector A, or let A be the point with coordinates 5 and 4. Let B be another coordinate, -3 and 2. The question says find the position vectors of A and B. Go further to find the vector AB, and finally find the magnitude of vector AB. We are told to do 4 things here. We're going to start one after the other. Position vector of A will be this representation in terms of your I and J. That is the position vector. It's going to be, because A is 5, 4. This is only how many dimensional? 2 dimensional. The dimension is X and Y. So we have X and Y, right? And then you have it as 5X, or you can have, no, 5X is 5 actually. 5I plus 4J. If you go back to the Cartesian graph, which I have here, you can see this is vector in the direction of X with unit vector I. Vy is in the direction of Y with unit vector J, and Vz is in the direction of Z with unit vector K. It's exactly what we are doing here. In this case, we only have 2 dimensions. Let's also obtain the position vector of B, since we have obtained the position vector of A. Okay, so this is the position vector of A. The position vector of B, therefore, is -3I plus 2J, because this is 2-dimensional. I believe you understand why that is the case. All right. We have answered the first two questions. The next question says, find the vector AB. To obtain vector AB, we need to be able to sketch out these coordinates. And that is what I've done in this diagram, but I will illustrate how that is done. If you look at the diagram, from 0 on the x-axis, from 0 to 5, that's the coordinate, that's the x-axis of, or x-coordinate of A. So it is to 5, and that is here. While the second, that's 5, 4, and the y-coordinate is at position 4. So you can see it's 4, it's 4, if you trace it, it's 4 up to this point and 5 downwards. All right. So that is it for A. So here, the blue line here is vector A. Similarly, for vector B, it goes from -3. So we have -3 and 2. So this is the point for B, and we draw the vector to that point. Don't forget to show the direction with your triangle or your arrow, and the same with vector A with the arrow. Now that we have these two, what is then the resultant of these two forces, or no, two vectors rather? The resultant, like we have stated before now, will be the dotted line between points A and B. How do we obtain that? The magnitude of this vector. Before we can obtain the magnitude of that vector, we need to first of all do the sum of vector A and B. The sum of vector A and B, which is, we can say is R, will be equal to vector A, right? So we're going A to B, and that's the resultant. So it's AB. So it's going to be A, it should be A plus B. That is what it should be. However, we're going to put something into consideration here. What we're putting into consideration is that the direction of vector A and B. What is the direction of vector A? If we're going to do AB, the direction here will then be opposite direction of vector A. So that would imply minus A, but the direction of B still remains the same direction. So it's going to be plus B. I hope you do understand that. This can also be written as, because it's positive B, that's B minus A. And that is how I have obtained this equation. Hence, we simplify. We already know the position vector of B to be minus 3I plus 2J. So I have it substituted here. Then the position vector of A is 5I plus 4J, which is what I have substituted. Then I do a subtraction between the two of them. I'm subtracting, don't forget our subtraction. I'm subtracting minus 3 minus 5I. Then I do a subtraction between 2 and 4. Hence, minus 3 minus 5I gives me 8I. 2 minus 4 is minus 2J. That is our resultant vector between A and B. Now we're going to go to obtain the magnitude, that is the length of that resultant vector. the length of R, which is the resultant vector, would be magnitude of R. Similarly, we're going to be using our triangular law or triangle law, which is our Pythagoras theorem. To do that, we have this magnitude will be the square root of x squared plus y squared. Beautiful. So what is our x? Our x, remember we have two vectors in this case now. So we're going to be having the magnitude, R is b minus a. So that becomes the magnitude of b minus a, right? And this will imply the magnitude of b1. Remember, there are two vectors involved here. That is why we are considering b1 and b2, a1 and a2. a1 is with respect to vector a. So from vector a, we're going to have a1, we're going to have a2, okay? And with respect to vector b, we will have b1 and b2, all right? So what we do from here is, because we're doing, the magnitude is b minus a, this then becomes b1 minus a1, okay, high, plus b2 minus a2. Don't make a mistake here. Don't make a mistake of doing b2 minus b1. No, it is b1 with respect to a1 plus b2 with respect to a2. All right, and that is how you obtain the magnitude. So this formula holds for you to obtain the magnitude. And what you just simply need to do here is substitute values. What is b1? b1 from this equation, from this position vector, will be what? Minus 3i. b2 from that position vector is 2j. Okay, same thing. a1 is 5i, while a2 is 4j. So you can simply substitute this into the equation which we have here. We're going to be having the square root of b1. b1 is minus 3 minus a1. a1 is 5 minus 5. Take the square. Please take note of this formula. I'm going to show you for maybe, please take note of this formula. I'm going to show you for maybe 3 coordinates and show you how to obtain that formula with respect to 3 coordinates. So B2 is 2 minus A2, 4 squared. That's minus 3 minus 5, it's minus 8. And the square of minus 8 is 64 plus 2 minus 4 is minus 2. The square of minus 2 is 4. Right? And then you can take the square root of that to obtain the final answer. So I want to show you something before I proceed with. Let me just show you one other thing. Don't forget to include your square root, because this is 64 plus 4, that's 68. So it's going to be root 68, which should be 8.25 or so. Permit me to share. I want to share something else. My blank whiteboard. Okay. And I want to consider 3-dimension so as to obtain a general result for 3-dimension. Okay. So in a 3-dimension, call it 3D. What's going on? In 3, I want to write. Okay. In 3. Sorry, this is not working well for me. Not working well for me. I'll just use my mouse. In 3D, how do we represent that? Suppose we have a vector A, which is represented as OA. Okay. And then you have it as a Cartesian representation, A1I plus A2J plus A3K. All right. And you have another vector B, which we can call OB. And we say B representing it in Cartesian, it's B1I plus B2J plus B3K. Okay, say we're given these two vectors. We know that AB from our example is B minus A. That's from the same example we just dealt with, right? And here we have this to be equal to B1. Remember, it's 3 coordinates now, minus A1. For 2 coordinates, we only stopped at J. So here we're going to go on to K. So it's B2 minus A2 J, and then plus B3 minus A3 K. All right, that is the vector AB. What is going to be the magnitude of this vector AB? The magnitude of the vector AB will be the same thing as the magnitude of B minus A, which is then going to be, oh, sorry, this is the magnitude, which is then going to be what? Up to K. So it will be the magnitude of B1 minus A1 I plus B2 minus A2 J plus B3 minus A3 K. This is a K, and then the magnitude of all of it. Sorry, I think there's a mistake somewhere here. Okay, it's a bracket for high. All right. Okay, so this is what we're going to be having as the magnitude of AB. But we can use our triangle law to simplify this further and to then abstain, because it's going to be the square root of what? B minus B1 minus A1 square plus B2 minus A2 square, B2 minus A2 square plus B3 minus A3 square. So this is how we do it for three-dimensional. We can extend this up to n-dimensional, which then would be plus bn minus an if it is n-dimensional. So it will be dot, dot, dot. Okay? And the square root will extend to that. So this is just a general way of representing our vectors, obtaining the vector and the magnitude for different dimensions in the Cartesian way. So from here, I want to stop sharing the whiteboard. I want to then share my files again. We would then go on to see scalar products. Let me just go back to my slide. Good. So we want to see scalar products of two vectors, or what we refer to as the dot product of two vectors. Two vectors A and B, how do we multiply them together as dot product? Remember at the beginning of this class, I mentioned that you have two different ways of multiplying vectors. You have the dot or the scalar product way, and then you have the cross product way. All right. So this dot product is what we're dealing with now, and I would interchange the word scalar product with dot product. Please, they mean the same. The scalar product, which is also known as the dot product of two vectors A and B in a two-dimensional space, is defined as A dot B equal to the magnitude of A times the magnitude of B cos theta. This multiplication or this product, they are not the same thing when you do cross multiplication. All right. The angle is the angle between the two vectors you are considering. I will show you. Let's just sketch out something now. Suppose we have suppose we have, I want to draw out the vectors. Suppose we have a vector this, and then you have another vector this. Call this vector A. No, let's do this. Call this vector A. Call this vector B. All right. The dot product of these two vectors A and B would be the magnitude of A times the magnitude of B cos theta. This angle is the angle between the two vectors. All right. So this is what I want you to understand by scalar product. Scalar product has the following properties. If you have vector A and vector B to be parallel vectors, then you have the dot product between them to only be the multiplication of the magnitude between the two vectors. Let's see. Let's just quickly see how that is true. Let's draw a parallel line for vector A and another parallel line. I will draw that. And another parallel line. So A and B are parallel to each other. Okay? What is the angle between these two parallel lines? Is 0. Then you have A, magnitude of A, and the magnitude of B from the formula cos 0. What is cos 0? Cos 0 degree is 1. Since this is 1, then we're going to be left with magnitude of A times magnitude of B. That is for parallel vectors. So we have been able to show this. Let's come to the second property. Suppose vector A and vector B are orthogonal vectors. You know, orthogonality means perpendicular. It means this and this, right? So let's call this vector A and call this vector B. When these two are perpendicular or orthogonal to each other, this angle between the two of them will be what? Will be angle 90 degrees. Since this is angle 90 degrees, what is going to be cos of angle 90? So let's come back to this equation. Say this is angle 90. What is cos 90 degrees? Cos 90 is 0. So that becomes 0. If this is 0, multiply 0 by the magnitude of A and B, you're going to have everything to be equal to 0. Hence, the dot product between vector A and vector B is always 0. We have proven that. You can also do the same proof for components or unit vectors. So for unit vector, if you have unit vector I multiplying unit vector I or dot multiplied by each other, they're going to be 1. The same thing for J, the same thing for K. The only time when this will be 0 will be when you're multiplying the unit components or vector I by J, I by K, J by K, and so on. That's the only time. So that means this will be perpendicular. This shows perpendicularity, while this will mean they are parallel. is the property of scalar product or dot product. I want to show you something more in terms of components. Suppose we have this vector A, and you know in components, in terms of component, A can be expressed as A1I plus A2J plus A3K if it is 3-dimension. If it's 2-dimension, it's A1I plus A2J. It's the same thing as saying AXI plus AYJ. This also for vector B, you can represent it as components BXI or B1I plus B2J or BYJ. So the scalar product between these two says that when you do a scalar product between the components, you are going to have it as AX BX, or you say A1. It could be written also as A1 B1 plus A2 B2. Okay, so you can also write it in this form. The scalar product can also be calculated using this formula, of course. So here what we mean is this, which is not in component form, is the same thing as this when we're dealing with component form. Okay. I will quickly show you for 3-dimensional components. Let's go to another. Let me share a whiteboard to do that. Let me share in terms of 3-dimensional components. I want to do a new one. I'm just going to be using what's going on here? Okay. For 3D, all right? What's happening? Okay. For 3D, I want to do a new whiteboard, so this permits me to just clean up this. It's the same one. I can use the same vector notation. So what we want to show is dot products in terms of components for 3-dimension. What I've just done is for 2-dimension. So let's see for 3D. All right. So for 3D, we have, suppose we have A to be A1I plus A2I, J plus A3K. Okay. What we want to do is to show that A dot B is equal to A1 B1. Remember, this is the components form, plus A2 B2 plus A3 B3. All right. So how do we do this? Dot product, we want to do a dot product between A and B. So we have A1 I plus A2 J, and we're going to be using the properties we have just studied, plus A3 K dot, so we're doing dot B1 I plus B2 J plus B2 J plus B3 K. So let's do a dot product between these two vectors. How do we do it? Take A1I. Just take A1I and multiply by B1, multiply by the vectors of B and by the okay. Then take an element of vector B, of vector A, so it's going to be plus A2 J multiplied by all of this vector of B1 1I. Okay, then take the third element in vector IA, that's A3K, and also do a multiplication of vector B. Okay. Now when you expand this, when you do this expansion, you see I, the most interesting part of it, which you want to look at, is I multiplies by I from the property that we know about scalar product. I dot I is 1. You see I multiplied by J, I dot J is 0. You see I multiplied by K, I dot K is 0. So we're going to be left with A. So we're going to be left with A1 B1 because I dot I is 1. Come to this second part. So we have plus J multiplied by I is 0. J multiplied by J is 1. So we have A2 B2. J multiplied by K by the property we described above is 0. Now let's come to the third part of the sum. We have K. K multiplied by I is 0. K multiplied by J is 0. K multiplied by K is 1. So we have A3 B3. And that is what happens in terms of components. So scalar multiplication of components gives you A1 B1 plus A2 B2 plus A3 B3. Scalar multiplication without components, you use the formula magnitude of A times the magnitude of B cos theta. Theta is the angle between the two vectors. I hope that is clear. Yeah. Now that we have seen how to perform scalar multiplication, we will be going on to vector products. Vector product. Vector product is also referred to as cross product. But before then, let's solve this example for a scalar product. Then we go on to vector product. Let's solve this example. This is an example of a scalar product. The question says, let vector A be 3i plus j minus k. This is a three-dimensional vector. And B, vector B, is also three-dimensional 2i plus j plus 2k. Find A dot B, that is the dot product between A and B. Also, find the angle between vector A and vector B. To find the dot product of this, we can simply do what? Use the component terms approach. And how do we do that? You know that we have three components in this case. All we just need to do is to use that formula A1 B1 plus A2 B2 plus A3 B3. So this is the formula we're going to be using. We're going to be using the component term formula. So what is A1 here? A1 is 3i. A2 is 1. So let's do A1 is 3. A2 is 1. A3 is minus 1, right? Now, let's go on to B. B1 is 2. B2 is 1, while B3 is 2. Okay, so you can simply substitute these values into the equation star. All right, so that would be A1, 3 times B1, 2. That is this part. Plus A2 is 1 times B2 is 1, which is this part. A3 is minus 1, B3 is 2, and that is what we have here. So we simplify it and we obtain 5. The next question is then we want to obtain the magnitude now. We want to obtain the magnitude. Remember, for you to be able to find the angle between the two vectors. The angle between the two vectors will be magnitude of A times magnitude of B cos theta, right? Cos theta. So we need to then calculate the magnitude of A. Magnitude of A using the triangle law will be square root of the square root of we need the magnitude of A, only the magnitude of A, not the magnitude of A and B. So it's the magnitude of A1 square plus A2 square plus A3 square, which is 11. Magnitude of B, which is the magnitude of only vector B. Magnitude of B, which is the magnitude of only vector B. That is the length of that vector, will be 2 square, that is B1 square plus B2 square plus B3 square. Right? So let me write that out. Is the square root of B1 square plus B2 square plus B3 square. Okay, and the same thing applies to the magnitude of A. Is the square root of A1 square plus A2 square plus A3 square. Okay, I hope you don't understand this. Now that you have been able to substitute the values, you've obtained the magnitude of A and the magnitude of B. Now we want to use our answers to solve for the angle between vectors A and B. This angle is the angle between the two vectors, which is initially the formula, and that is A dot B, which is equal to this formula, magnitude of A times magnitude of B cos theta. We have obtained the magnitude of A, we have obtained the magnitude of B. We have also obtained A dot B. All we need now is to obtain the angle. We can simplify by dividing both sides by cos theta, we divide both sides by the magnitude of A and B to be able to obtain our cos theta. So if you divide both sides, we're going to have this equation, right? When we have this equation will help us then to obtain the angle between these two vectors. Just substitute A dot B is 5. Magnitude of A is root 11. Magnitude of B is 3. When you do this arithmetic, you take the arc, that is cos inverse of what you have here, and this will give you the final answer. So that is how we work around scalar product. We are going on now to the vector product, also known as cross product. This vector product of vector A and vector B in a three-dimensional space will be defined as follows. We would be using this equation to define the vector product. Each of the terms are familiar. The only thing that is included here is n, and n is the unit vector perpendicular. Please pay attention. N is the unit vector perpendicular to the plane containing A and B. When you talk about perpendicularity, remember that for perpendicular, we say I dot I is 1, K dot K is 1, J dot J is 1, and then all of that. But for vector product, we're going to be looking at something slightly different. It's a bit cumbersome, but please pay attention. The properties of the vector products are followed. If vector A and B are parallel, by now you should be able to describe parallel vectors yourself. Say this is vector A, and if it is parallel, it's parallel to vector B, right? Then you have A plus B to be 0. You can also prove it using the formula of the formula above. If you have A, that's the magnitude of A multiplied by the magnitude of B sine theta times n, which is the unit vector. We can do this. What is theta for this case? Theta between these two is what? Is 0. So what is sine 0? Is what we'll use in this case to simplify it. So if you do sine 0, it's going to be 0, and 0 multiplied by this is 0. That's the cross product of parallel angles. All right, let's go on with component terms now. Unlike scalar product, where I dot I is 1, j dot j is 1, k dot k is 1. For vector product, I cross I is 0, j cross j is 0, k dot k is also 0. Other products or properties which we would be using for calculation will be your I cross j, which will be k, j cross k is I, k cross I is j. And in most cases, we say these are your n or the unit vector that is perpendicular to that space, to the plane which contains your A and B, which contains your both vectors. So you can also have all of these properties. Please study it. Let's see if we have examples. Okay, for component terms, similar to scalar product, the I, j, and k terms vanish. You'll only be left with A1, B1, plus A2, B2, plus A3, B3. But for vector products, that is not the case. For vector products, in terms of components, you are going to be having A2, B3 minus A3, B2. So let's see how this works. Let's just see how these general terms, how we arrive at this general term. I will just quickly show you. That's why I said it can be cumbersome. But later on, you'll see we have a different approach to this for obtaining vector product, which is quite straightforward and easier than this approach. Okay, let me just go straight to that approach because it will help you to be able to simply obtain vector products. The approach is called using determinants. I know some of you don't know what determinant is. Determinant is a way of simplifying a matrix. However, I'm just going to introduce it to you here, but when we get to matrices, I will describe it in details. How do we use determinants to evaluate vector products? Vector products, recall again that it's a cross, it's not dot, it's cross. It can be evaluated in this form. You write the ijk components on top of this matrix. Okay, so what you want to do is you want to represent your components and the terms in the component of the components in a matrix form. So if you have 3 dimension, you're then going to be having the ijk, right? Let me write it out. For a vector A, you have A1 I plus A2 j. This is the component representation plus a3k, right? This will be your a. And then you have your b to be b1 I plus b2 j plus b3 k. All right. So this is what we want to represent now. You I, j, k. These are the unit vector space. So we have them written first. Then you have a1. So we have I, j, k. Then you have a1, a2, and a3. Okay. Then you have b1, b2, b3. Okay. So we're going to be using this approach to evaluate vector product. How do we do it? I'll show you now. Take I. Take I. All right. Then close up the column which you have selected. So I've selected I. So I'm closing this column. You can pretend to use your hand to close it. And then you also want to close this header. All right. So you are left with A2, A3, B2, and B3. So write out the I which you have selected. Then you want to perform some kind of arithmetic with A2, A3, B2, B3. So we do this form, cross. So you do A2 times B3, A2, B3. You see that? Minus A3, because you are doing a cross, A3, B2. All right? We're not done. We're only done with ith component. Let's now go, now we're done with ith component. Let's go on to jth component. So I'm going to draw another matrix. It's not drawing. So let me just draw another matrix so I can do a cross properly with that. This is I, this is J, this is K. Okay, so it's A1, B1, A2, B2, A3, B3. Okay, so now we are picking J component. Okay, so now we are picking J component. We are done with ith component. So since we are picking jth component, we pretend to close the jth column. All right. So we're not doing, it's usually the sign is usually plus, minus, plus, and so on. All right. So the next will also be minus, and so on. So that's usually the sign. So that's why we have a negative. It's a standard way of doing it. So pay attention. Now we have picked J. It's going to be J. And then we're going to be, since we have closed this column, second column of J, we would then be dealing with A1 and B3. So it's A1 times B3 minus, we're dealing with A3 and B1. A3 and B1. You see? So I'm done with that J part. Then I'm left with the last component, which is K. Remember I said it's plus, minus, plus. So it's plus K. And then let's now go to the table. So we are done with this. We are picking the k's. So it will be A1, B2 minus A2 B1. And this is how you simply represent or evaluate your vector product. Here we have done it for 3 components. You can practice to do more, and then you see how easy it is. Let's practice this final example before we wrap up today's session. The question says, find the vector product of A, vector A, 2i in this component form, 2i plus 3j plus 7k. Vector B is given in this component form, B is I plus 2j plus k. How do we obtain the vector product? Remember, your vector product is the cross product. So we want to obtain the vector product between vector A and B. And the easy one is to use this determinant approach. Using the determinant approach, you just draw I, J for each of the components. A is 2, is 3, and is 7. All right. For B is 1, it's 2, and 1. Fine, beautiful. So let's pick for I. We will take I, then we close that column for I. So it's 3 times 1, 3 times 1, right? Minus 7 times 2. Minus 7 times 2. So that is it for I. Then we go on. Remember, it's plus, minus. So it's minus j. Then we close the column for j. Is 2 times 1 minus 7 times 1. Right? Now we're done with j component. We go on to the kth component, plus k. Now it's plus k. We close the column for k. It's then 4. That's 2 times 2 minus 3 times 1. All right. Now let's simplify. 3 times 1 is 3. Minus 7 times 2 is minus 14. So we have this part, I. 2 times 1 is 2. 7 times 1 is 7. So we have 2 minus 7, this part. And then 2 times 2 is 4. Minus 3 times 1 is 3. So we have this part. And when we simplify, we come we have minus 11i plus 5j plus k. That is a vector product, and that is how easy it is to work it out. It's using the component form which we initially did. it's cumbersome because it has to do with I and j. Initially, for scalar product, you have I dot I to be 1 and makes things easy. I dot k is 0, but it is not the same when you're dealing with vector product. So that is why we have ended up using determinant approach to evaluate our vector product. I believe this is helpful, and I'm going to end this class here. Please go over it, and feel free to ask your questions when need be. Thank you, and bye-bye.